Okay, so this is lecture 23, section 4, ensemble models, and this is module 4. So in the previous 4 modules, we covered back decision trees, random forest, and stacking. So in this last module of this ensemble lecture, we will talk about a really powerful family of models we relied upon the boosting approach. Okay, let's get started.
So now let's talk about boosting. Boosting, you can think about it just a specific kind stacking approach that is very smart. It's a very smart kind of more inclined. It's designed very specifically to, it fits decision tree very nicely. Yeah. So yeah, I copied these examples from somewhere. Like, let's see if this makes a point. So you try to classify the real apples versus plastic apples, and then you really try to make super simple. You try to learn super simple decision rules as base learners. In this case, my base learners are mostly very super decision rules. So maybe just one layer of decision rules. Some people actually call that decision stump, right? Will be one layer or 2 layers or maybe just a few layers. So if I have, let's just write them as shallow decision tree. What's the issue of shallow decision tree? What's the property of shallow decision tree? Bias and variance. So the shallow decision tree has the property of
high bias.
Yes, high bias. All right. So then you sequentially train a base classifier to correct the mistake of previous rules. So now we don't do bootstrap of my training data. I just work on the same training data, but I'm training a sequence of base classifiers. So I don't, like before, I'm doing parallel type of parallel type of decision tree training, right? It's just one tree, Fi versus Fj, they really don't dependent on each other at all. It's completely independent. But now I do this procedure sequentially. And every step I focus on hard examples, and I'm giving higher weight to better decision rules that I learned. Okay, so I have training data, and then I try to learn using the Olin thresholding function. Olin thresholding. So I can even have this type of linear classification because I only allow thresholding operations, which is what? Thresholding operation on this figure is either this or either this, right? There are only 2 kinds of rules, either thresholding the color x1 or thresholding the weight x2. So this is the only 2 type of rules I'm allowing, which is super high bias, right? How can I figure out a best decision tree or decision functions using only these 2 kinds, either thresholding on the x1 or thresholding on the x2? All right, so first simple rules based on loss function, right? This is almost the best you can. Almost the best, to minimize the training loss, because it's only allowed to do thresholding. So this is the best you can, but it makes mistakes on here, makes mistakes on there. So now I focus on this and that. Okay, so now I try to relearn, but I emphasize this 2 should not make mistakes. And now this 2 doesn't make mistakes anymore. Okay, so this is the second rule I learned. I only allow either this thresholding or this thresholding. Okay, this is all follows what I allow, right? But it's super high bias based learner. All right, now I'm making mistakes on this and that. I emphasize next time, please correct this too. Now I'm learning further. Yeah, so this got predicted correctly, but this actually not. But this got predicted correctly. This amount on my X3. All right, so then there's a huge amount of examples not predicted correctly from X3, right? Now I'm learning X4. I want to predict all of those correctly. This is X4. So in the end, and there's all this X1, 2, 3, 4. They're all super simple decision rule. And then the final classifier is a combination of the 4 by treating different decision rules with different weights. And this is what you get from AdaBoost. So what you allow in the base learner, it's very, very rigid. It's only allowed to threshold this direction or thresholding that direction. But the combination can give you very flexible decision boundaries. So how do you do this? So first, you have a weight on each samples. Sorry, I'm a little slow. Let me quickly go over that, but the figure tells you almost everything. You learn the best base learner by optimizing the current loss. And then this is the decision, this is actually the definition of that loss. It has the weight from each example. Each example is treated differently in the loss calculation. And this is a very key point about this loss function. And also, you are assigning weights for each base learner. So this is our additive summation of different base learner, but that weight is actually learned. It's controlled by this error you just get from the specific base learner you just learned. And the final, and also you are updating the weights on each example based on your current predictor. If it's made a wrong prediction, you're going to give the really high weights on those examples got predicted wrongly. And the final classifiers is this summation of alpha t times all the base learner. So there's actually a lot of theorem behind why the choices of the weights of examples, why the choices of the weights of classifiers, which I have a lot of extra slides if you want to read those. All right, so sorry, it's kind of quick. So there's only one thing I want to talk about is boosting versus bagging. So similar to the bagging, boosting reduces the variance because the ensemble. And unlike bagging, boosting fit the tree to the entire data and adaptively weight examples. And boosting trying to do better at each iteration. It's trying to do better at each iteration. In fact, so even though each base learner has high bias, but your blended learner, it's a summation of alpha t times all the base learner, right? That blending, in fact, reduces the bias because it's trying to be more and more complicated. So the blending is more, so each base learner covers something your previous learner, everything touches so far, not covered. It makes the whole model space slightly grow at each iteration. All right, so I don't have time for XGBoost. So XGBoost, in fact, so you can tell from this algorithm in AdaBoost, this is all specific design, right? So in learning the HT and also the alpha, it's specifically only related to the area. However, you actually can use gradient to get even better estimation of alpha, and what you can use gradient to guide the next learner, not just so there will be extra slides. Great, so thank you.